Hello and welcome to lecture number 16 of CS 531 Memory Systems and Architecture. This is the first lecture that I am uploading after midsem. Your midsem paper will be evaluated by this week and you will get your answer script by 5th of April. So I hope you already received the answer script of the quiz 1 and quiz 2. So as I have mentioned in my in a video before midsem, that after midsem there will be two regular quiz that I have already announced. So that will be quiz 3 and quiz 4. And instead of these two quizzes, there will be three more quizzes. Those quizzes will be very short quiz. Maybe I'll give you hardly 10 or 15 minutes time for each quiz, and this quiz will be, first two quiz will be for 2 marks each, and the third quiz will be only for 1 marks. So here, so you have to prepare for at least one quiz after every week. So these quiz 3 and quiz 4 are important quiz. So quiz 3 and will be most probably by after 3 weeks of pre midsem, and then I'll take another quiz, that is quiz 4. There is no change in it. But the other three quizzes, that is the 2 marks, 2 marks and 1 marks quizzes, those quizzes will be conducted after every week. And my main intention here is to force you to study my lectures. Yes, I have to force you because I can see many of you are not following my lectures. So every week there will be a quiz. So if you want this extra 5 marks, you have to study, you have to follow my lectures regularly. Okay. And regarding your term paper, I hope you have decided, and by tomorrow afternoon you will receive a email from my side where you have to select your areas. And I'll encourage you all to select areas like replacement policies, then DRAM or prefetching. So these areas will be easy for you to implement. For example, if you go for replacement policies, you have a simulator called GemSim where you can easily implement it. If you are going for DRAM, then you have a simulator called Remulator, where you can easily implement your proposal. And if you need help from DRAM simulator like DRAM sim or Remulator, then we have our MTech students who can help you. We have our means MTech senior students who can help you in simulators. But yes, if you have if you know any other area, and if you are interested in any other areas, then I'll not stop you to work in that areas. This is just my advice, that if you follow this particular this selected topic, then it will be easy for you. But if you are interested and if you want to work in any other areas, you will be always welcome. So don't think that I am forcing you to do in these areas. This is just an advice. Okay. So what we will do in this week we'll discuss about utilization issues of cache memories, last level cache. After this week, from next week, we'll consecutive 3 weeks we'll discuss about the main memories. Our whole discussion from next week will be on main memories. First we'll discuss about the different timing signals about DRAM memories, and then we'll go for how to reduce the refresh overhead of main memories. Then we'll discuss some attacking technique that is called row hammering technique. So how to handle those row hammer attacks, and all these things we'll discuss. After that, we'll discuss about hybrid last level caches. We'll again come back to cache memories, and we'll discuss about hybrid last level cache. After discussing hybrid last level cache, we'll go to hardware securities, and then we'll again discuss about some security issues in cache memories. After that, if time permits, we'll discuss about prefetching, and then we'll stop this course. So the exam wise, the load, I can say that the load will be almost similar as pre midsem. I'll not give you much load. So every week I'll follow the same policy, that I'll not give you load of more than 3 papers every week. That policy I'll maintain. So load wise, yes, it will be same as pre midsem, but yes, I'll try to force you to follow my lectures, and that's why I'm taking some extra quizzes. Okay. So let us start with our today's class, utilization issues in last level cache. So the basic introduction about these utilization issues, I think I've already covered it before midsem. There was, I think, in one or two lectures I've explained what is called local utilization issue and what is called global utilization issue, but I never discussed any existing technique or any existing research work which can prevent this type of issues or we can resolve this type of issues. So I have not discussed any research paper. So in this week we will discuss this, what are the existing solutions, what are the existing techniques so which can be used to remove this type of issues, and what are the positive side and what are the negative side of these existing techniques. So all these things we'll discuss in this week, and at the end of this week you'll realize that though it looks a simple problem, but still there is lot of scope to improve the existing solutions. Okay, so we'll throughout all the lectures of this week will follow this simple architecture. Again, I think this architecture it's very common now because I am using the same architecture from the beginning of the course. So so there are 8 tiles here, sorry, 8 cores here, and all the core are sharing a common large size LLC, shared LLC. So but we don't want a shared LLC like this. What we want is the shared LLC must be divided among multiple banks and it is distributed like this. So this bank are actually shared LLC. So this shared LLC is actually, it is still shared here, but it is now divided among multiple banks, and each bank is associated with a cache, with a core, right? So this type of design is also called TCMP. So I have already explained many times what is called TCMP, but again, if you want to understand what are the concepts that I'll discuss in this week, then this slide is important. You have to understand what this diagram is saying. And one point you have to understand, this each bank here, these banks are actually set associative cache. Every bank is a set associative cache, that you have to understand, that each bank is a set associative cache like this point is very important. Okay, and then the mapping policy of TCMP is also important. If you forgot this SNUCA concept, then please repeat it. I hope you were able to solve the last question of midsem. The last question of midsem was based on TCMP and its mapping policy. So if you have solved that last question, then I think the mapping policy of TCMP is clear to you. But that mapping policy is based on SNUCA. So in this week we'll discuss another mapping policy based on TCMP, but let us not make it complicated today. So we'll discuss it on the third day or maybe on second lecture. Okay, so till now I am following the same mapping policy in TCMP that I have discussed before midsem. Okay, so utilization issues, there are two type of utilization issues: local utilization issue and global utilization issue. So again, you have to remember what I said, that each tile, each bank here, each tile has a bank, right? And this is a shared LLC. So if I have already explained in my previous slides, I am not explaining it here again. So local utilization issue means each bank, since it is a set associative cache, it has been found that the sets are not using uniformly. So for example, if this is a set associative cache, or I can say set associative bank, so we know that how, for example, if requests are coming from this code to this bank, so there are many requests coming, r1, r2, r3, like this, then we know that how this request or this block requests are mapped to this associative cache. It's based on a bank index, right? So it may be possible that all these requests, most of the requests are going to this particular set because of or their bank index is mapping to this particular set. So it may be possible that this set is heavily loaded. There may be some other set like this, means consider that this set is also heavily loaded and this set is also heavily loaded, but you can see that these and these two sets are almost ideal. So this type of problem is quite possible in set associative cache, that some of his sets are heavily loaded, they're facing more conflict misses as compared to some other set which are almost ideal. So this thing is shown in this graph. This claim that I'm the concept that I'm claiming here, that is showing here. So in this graph, this side, these are the number of sets. So this is a this experiment has been done on a cache where there are I think 512 sets. Okay, so you can see in this direction there are 512 sets, and in y-axis you can see this is the number of conflict misses. So you can see that the number of conflict misses in each set is not uniform. You can see there are some sets here which have very high conflict misses, and you can see there are some sets where the conflict miss is very low. So it means that these sets are highly used sets, and these are lightly used sets. So it means that the each bank, so here I am not talking about the entire cache here, I'm saying I'm discussing only about a particular bank. So this set associated bank is not utilizing properly. Why it is not utilizing properly? Because if I go again with this small architecture, so this set is heavily used, this set is heavily used, and this set is heavily used. Okay, but there are two sets which are not at all using or almost ideal. So it means that the entire cache space of this bank is not utilizing by this application, right? So the that issue is called local utilization issue. So there are many techniques that we will discuss in this week, that how to use the entire cache space uniformly, or this entire cache space uniformly. So there are multiple techniques we will discuss, or they propose different ideas based on which you can utilize the entire cache space uniformly. So what is the plus point of this? If we can utilize the entire cache uniformly, so what is the benefit means we can reduce the number of misses, right? So if we reduce the number of misses, you know what how the performance will improve. So I am not going that in that explanation, but if we can improve the utilization, yes, we can remove the number of misses, and that is our main agenda here. So that is actually about local utilization issue. And global utilization issue, I think I have already explained. Global utilization issue means there are multiple banks here also possible, right? Each L2 cache is there is a bank here, each tile there is a bank, right? There will be a bank here, there will be a bank here, so there will be 15 banks also. So it is also found that the banks in the last level cache are also not uniformly used. Some banks are heavily loaded and some banks are lightly loaded. Why again this is possible? Because if you remember the SNUCA mapping policy, first it looks for a bank index, it goes to a particular bank, and then it looks for a SAT index, right? So if most of the requests based on their bank index is going to a particular bank, the load of that bank will be much as compared to other banks, and that is exactly happening. And if you see this diagram, if we see this diagram here, it is uh, just 1 minute, yeah. So this side it is the number of banks, B1 to B0 to B15. There are 16 banks, and you can see this is the number of loads in this bank. So you can see the load is not uniform. There are some banks here which are heavily loaded, and you can see there are some banks which are very almost ideal or very lightly loaded. So it means that the utilization issue is still there, but we are calling it global utilization. Global utilization means the banks are not utilizing properly. So there must be some technique by which the banks must be using properly. Otherwise the spaces there are the spaces in some bank are wasting while when the other banks are facing shortage of space. So these are the two main issues of in utilization issue in LLC. So if we design a flow chart for this, then if we go for effective utilization of TCMP, means how we can efficiently utilize the last level cache of TCMP, then we have to solve two things. One is called local optimization, and one is called global optimization. So if we go for local optimization direction, then we'll discuss few papers. The papers are VUE, SBC, Zcache, and FSDAM. These are the papers that we will discuss. There are some other papers also exist, but we'll discuss these four. And if we go to global so this is called dynamic associative management, that I'll this term I'll discuss now. And if we go to the global optimization side, then we have we'll discuss about two paper, TD NUCA and TLD NUCA. So these are the papers that we will discuss. So starting from this side, dynamic associativity side, that is the local optimization side, we'll first discuss, this is the paper called BUA, and then we'll discuss this paper. This paper is actually FSDAM 3 FSDAM, and then we'll discuss Zcash. We'll also discuss SBC, which is this paper. But since if I also give this paper as in for exam, for exam, then there will be four lab papers in this week. So what I am doing, I'm excluding this paper from your exam syllabus. But this paper is very interesting paper, so you can read it if you want to do a term paper in this area, or if you want to do further research in this area, then you always read this paper. This is proposed in 2009. So you can see this VUA is the oldest one. It is proposed in 2005. Then SBC proposed in 2009, Zcash proposed in 2010, and the FSDAM is proposed in 2017. This is our work. In fact, it was a paper that I published during my PhD. And if I go to the right side of that is global optimization, then we'll discuss two paper, TD NUCA and TLD NUCA. But these are not important for your exam, but I'll discuss it here for in one lecture, and this is just for completeness purpose. Plus, if you again if you want to do research in this area, then these two paper will be important for you. So I'll discuss this. So you can see here this global utilization. Here I am only discussing my papers. Why? Because during my PhD I found that at that time there was no such specific no such paper which was specifically handling global optimization issues of TCMP. So that's why I could not able to find any other paper. So that's why I'll discuss only my paper. But there is a paper that I discussed in last week, just before midsem. That the paper was called Delta. Again, I told that the paper Delta was not included in your midsem syllabus. But if you read Delta, don't read now. After reading all this concept of this week, when I will explain you local optimization and global optimization, after reading all this thing, if you read Delta, you will find though the paper Delta that is saying about cache partitioning, but actually it is a combination of local and global optimization. So here I'll not explain you local so yeah, the ideas that I'll explain in this week are either optimizing local issues or optimizing the global issues, but not optimizing both, right? But if we go for that paper Delta, if you read it, then you will realize that they are kind of means optimizing both. So it's a combination of both things. So you can read Delta again if you want to know more about these areas. Okay, so let us start with the first technique, VUA. But before moving to VUA, what is this term, dynamic associativity management? This term is, I think, also important to explain. So to understand dynamic associativity management, let us go to the next slide, and then first I'll explain what is called DAM, and then I'll start with VUA. So to explain dynamic associativity management here, so this is called DAM, dynamic associativity management. So this means, suppose this is a four-way set associative cache. So if it is a four-way set associative cache, then as I said, it may be possible that some sets are heavily loaded. For example, these two sets are heavily loaded. It may be possible. So somehow when executing, if you can give more ways to these two sets, at present every set has four ways, right? This is a four-way associative cache. But somehow if you can propose a technique when dynamically you can give more ways to this set, because this set require more ways, because it's a heavily used set. So instead of four ways, if suppose this is an ideal set, so these two ways you can also allocate to this set, right? And the same thing here, suppose this set is heavily loaded, so this set plus these two ways of another lightly used set, you can assign to this particular set. It can improve the efficiency, or it can reduce the number of conflict misses of that heavily used set, right? So what you are doing here, if you allow it, so it means that you are increasing the associativity of set 0. If this is set 0, so you are increasing the associativity of set 0 from 4 to 6, and you are decreasing the associativity of set 1 from 4 to 2. So that's why I give a name. So this name is given by me. This is called dynamic associativity management. Means we are managing the associativity of a set associative cache dynamically. Okay. Now with this idea, I'm removing all this, because let me now explain the concept of view. What is called view? So before discussing view, you have to understand one more concept that also I think I have explained before midsem, that every set associative cache has actually two parts. First part is here, this is called tag part, and then this is the data part, right? And both have same kind of entries. Suppose if it is a four-way associative cache, suppose, so it's a four-way associative, board will be like this. So here only tag and some other information will be stored, and here data will be stored for each block. So whenever you want to search a block, you will search. Suppose you want to search in this set, you will search here, and if there is a hit, suppose there is a hit here, that means the tag stored in this position and the tag coming through the requested message are matching. That means there is a hit here. So if there is a hit here, then there is a one-to-one mapping with this and this position. So you'll go here, collect the data from here. So this is how a set associative cache works. Okay, so I think this point I have explained you before midsem also. So what BUA did is what they did. So their main intention is again this dynamic memory dynamic associativity mapping, DAM. Somehow they want to do this in view, that if there is a set which need more ways or more cache space at some time, then it can we should allow this set to use more ways. So how they do it, they use a simple technique. The technique is that instead of using this type of tag where the number of entries in tag and number of entries in data are exactly same, and there is a one-to-one mapping here, instead of this they use a different kind of tag storage here. This is the tag storage. So you can see there are number of ways in each set in tag storage is double than there. Here you can see there are 4 ways, right, in data storage, and you can see here there are 8 ways. 8 ways. So the number of entries in tag storage is also double than the number of entries in data storage. So the obvious thing is that all the entries in tag storage cannot be valid, right? If for example, if you are storing a tag here, suppose tag is t1, then corresponding data is here d1. So if you store another tag here t2, and corresponding data maybe here is d2, for example. So if you can do like this, then since the number of entries here in tag storage is twice the number of entries in data, so it means that only half of the entries in tag storage can store valid information at a time. Because valid means if you are storing an information in tag, then there should be a corresponding data stored in data storage, otherwise there is no meaning of that tag, right? So that is very important here. So then the why they have used it, why they have taken a tag array of double size entries. So their purpose here is, if here, so previously our tag was like this, right? For you can see here the tag. So but now the number of entries here is more. So if there is any set which is heavily used, that it can use all these tags, all this tag, and correspondingly they will use some data location here also. Maybe this location, all this location maybe will assign to this particular set at a time. And in this case maybe there will be some other set here which is ideal here. Suppose this set is ideal, so it means that the corresponding data location that is for this particular set will not be used. So we'll use all this location for this tag, sorry, this tag set. So this is their main idea here, that the idea is that we'll use double size tag array, and this double size tag array will help us to increase the associativity of a particular set whenever it is required. So now suppose there is a request coming from the core. Suppose this is the core is requesting for a particular block, suppose b1. So we first suppose b1 is mapping to this set, so we'll start searching b1 here. And suppose there is a b1 tag of b1 is t1 and it is matching here, suppose. So if it is matching here, then we can say yes, it is a hit. But when it is a hit, if previously there was a one-to-one mapping of this tag location to this data location, but now that one-to-one mapping is not possible, because previously the number of here the tag and data, the number of entries were same, right? But here the number of entries here is twice, so there is no one-to-one mapping here. So the what this BUA is doing, in each tag array they are storing some pointer. So there will be a forward pointer, FWD pointer. So if there is a hit here, based on this forward pointer, we will know that in which which data array location the will find the corresponding data. So suppose here, if it is, suppose it is written that 0, maybe we'll go here and we'll find the data is stored here in this location. So the point here is that by allowing a particular set to increase its associativity, what they did, they completely remove the one-to-one mapping between tag array and data array, and now they are using this type of things, tag and forward pointer and backward pointer. But so here in every tag storage they are storing the tag as well as a forward pointer, and in every data entry they are storing the data as well as a backward pointer. Backward pointer means the pointer of this location of tag array location. Both are important here. So this is how they are doing. But one problem here is that or we can say one challenge. There are many challenges in this work, but the first major challenge is now the all any tag location here. Suppose this one, if I want to store another, suppose I want to store here tx. Okay, so now the corresponding data can be stored in any of this location which is currently available. Any of, there is no restriction. So at this point, suppose this point this data is available, so this location is available, so I'll store the corresponding data here dx, and the mapping is maintained between the forward and backward pointer. So that's not a problem. But the problem is the entire data array is, from this entire data array, how you will find out that which block is free, and if no one is free here, everything is full here, then how you will maintain a replacement policy, because now the number of entries is much more, right? Then in that case, which block you will find out and which block you will select as a victim block here from data. So that is a challenging task. So if you read their paper, you'll find that they proposed they propose an alternative replacement policy that is called global replacement policy. They say that the overhead of that replacement policy is low, and based on that replacement policy they will replace a block from data array whenever it is required to remove. Okay, so this is all about vua. If you want to know more about vua, I'll read the paper. Also I'll give you a pdf where the vua and the set balancing cache as well as z cache are written in short, so you can read that paper also, that short document also. Plus I'll advise you to read the paper, the vua paper once. The idea is very interesting, though it is proposed in 2005, so there are some limitations. So before moving to next technique, let us discuss the major limitation. Of one limitation is implementing replacement policy, that I have already explained. Some other limitations are using forward and backward pointers. So whenever we are using forward and backward pointers, that means we need some additional storage to store this forward and backward pointers. So this additional storage sometimes creates a problem. The next technique is called SBC. So this, as I said, this the concept of SBP is not in your exam, but yes, it's a very interesting concept. You can read it from the paper also if you want to know it in more detail. Here I am explaining it in short. So SBC, they maintain several counters, so the number of counters are more as compared to vua. Here there will be multiple counters in this side as well as in this side. For each particular side there will be different counters. and based on this counter, dynamically they decide that which set is heavily used and which set is lightly used, and they dynamically make a combination, or you can dynamically make a group. For example, if after some time they find out that this first set is heavily loaded and second set is lightly loaded, so they make a group of these two set. And in same way, if they found that the last two set are this one is heavily loaded and this is lightly loaded, then dynamically they will make a group here. So the purpose of this group is now the heavily used set can either store its data here in first set, or also it can store it in the second set. Here also, if this set is heavily used, then it can store its data here, as well as it can store its data here also. So now the main question is how to search. So they say that searching is sequential. Searching is sequential means if there is any request coming which the block the data is mapping to set this set 0, then since that now set 0 is grouped to its set 1 also, then the searching will be sequential, means first it will search in set 0. If the block is not found in set 0, then we have to search set 1 also, and after searching set 1, then only we can decide if it is a hit or miss. So in summary, this is their idea that I have explained here, that dynamically they assign a heavily used set with a lightly used set, and sometimes they also check that if a particular set becomes, after some time this particular set become very heavily used, so they disassociate this association and disassociation rules are mentioned in this paper. So it after some time this group may be removed. In that case, all the blocks of set 1 or set 0 will only map to its own set. Okay, so if you want to know more about this, you read this paper. So here the main disadvantage is whenever you want to search a data from heavily used set, you have to search all the group sets sequentially one after another. So it may if there is a hit, then it is fine, but if there is a miss, then for miss you have so detecting the miss, it takes some extra time. So that is the only disadvantage of SBC. So SBC was proposed in 2009. Now I'll explain you another idea that is based on called Zcash, which was proposed in 2010. But Zcash is different from all these ideas because Zcash is not based on set associative cache, because set associative cache maintains a particular what you can say mapping policy, right? That every time there is a block request came, first go to a particular set and will search in the particular set, right? That is called set associative cache. But the Zcash is based on skew associative cache. Skew associative cache means it use a different hash function, and that based on that hash function they maps the block in different ways. For example, here they map it wave wise. Suppose this is wave 1, wave 2. Now I'm not explaining SBC, I'm explaining Zcash. Okay, wave 3, wave 4, suppose. So now there is a block. Suppose if the block is placing here, suppose the block is a, if the block can be placed in this position of wave 1, then it may be possible that block is you can place the block here in wave 2. And if you want to place the same block A in wave 3, then for example, suppose it may be a different location, suppose this location. And if you want to place the same block in wave 4, then maybe the location will be this. So they apply a hash function, and based on this hash function each particular block is assigned to a particular, this is called V or column, a particular position. If it is 1 here, then maybe in W3 it is 2, in W2 it is 3, and in W4 it may be 4, like this. So I have no slide for this, so I'll go to that paper, and from that paper I'll explain you what is called Zcash. This is the paper of Zcash. In short, I'll call this paper is Zcash. Okay, that I forgot to mention that there are two papers I've discussed. The first paper that I say VUA, the short name of that paper will be VUA. So every time I say VUA paper, you have to understand that that paper only. The next paper I said SBC, so that is the short name. So now here in this paper I'll use Zcash as the short name. So this is the short name, Zcash. So as I've said, this is proposed in 2010, and then it is published in Micro. So I'm not explaining all these details, but if you want to do some research in this area, I'll advise you to read it. There is nothing you will find nothing new here. Whatever concept I have explained, you'll see that all these things are written here. You will find this very interesting. again, not just this paper, whatever I have explained in this course, based on this, any paper that I am sharing with you, if you read them from the beginning, you will I'm very sure that you will understand it, and that will increase your interest in this area. If you just follow my whatever paper and the section I am giving you, that will be enough for your exam, but you will not gain much interest in this area. And that in this way you cannot also propose a better idea in your term paper also. But if you read this paper, whatever I am sharing you from the beginning, from the introduction section, line by line, you will understand that whatever concept I am discussing throughout my course, this is actually written here. Maybe they will write it in more detail, so you'll find it interesting. And while reading any paper, if you find any difficulty or any part which is not clear, then you can always ask me by email, or you can ask me in Google Classroom also. So instead of explaining all this thing, introduction and background, I'm directly going to a figure from where I'll explain you the concept of Zcash. This is the figure. So first, before going to Zcash, I'll explain you what is called skew associative cache. I think I have explained skew associative cache in the PPT previously, but in here, based on this diagram, I'll explain it again. So suppose this is your cache. So this it is showing here. This is the cache. Suppose, so there are three ways in this cache, and these are the there is no concept of set here, so you can say these are the position in each set and number, like this 0 to 7. And now if there is a request coming for y, you can see all these current blocks of current entries of this cache are showing here. Now a new request of y is coming, so there will be three hash function here, one for each way. This is for way 0, this is for way 1, and this is for way 2. So if when for y this h0 is giving 5 means way 0 5, which one is 5? This. So in way 1 y can be placed here, and in if we go for way 0, if we go for way 1, this hash function is giving 4. So in way 1 you can place it here, and in way 2 you can place it here. So since the cache is full now, and if you want to place y, then according to skew associative cache, you have to remove either a, d, or m. So which one can you can remove? You can remove the if your replacement policy you want to maintain is LRU, then you will maintain the oldest one among a, d, and m, and you will replace it with y. This is how skew associative cache works. So I hope it is clear to you. The only thing that I am not explaining are the hashing function. You may say that, sir, what hashing function they use. So for that, you read the paper of Zcash, you will understand that what are the hashing function they are using. So, and I think this is what there is nothing new here in hashing. You know what is called hashing and how to use efficient hashing technique. So I am skipping this part, but if you read this paper, you will find out what hashing technique they are using here. But the main point here is, if you want to place y, then in way 0 it is conflicting with a, only in this position you can place, you cannot place it in any other position of way 0. So a, d, and m, any of this you have to remove, and in that position you can place y, right? This is what calls skew associative cache. Now in Zcash, what they are doing, they use the same technique but for multiple levels. So here you can see that for y, the direct replacement candidates are a. You can go for this. The direct replacement candidates are this a, d, and m. That part is clear to you, right? But now when instead of removing a, suppose I don't want to remove a, because suppose okay, I'm explaining it again from the beginning. So if I want to place y, then suppose I want to remove, suppose I have to remove a, and in place of a I can place y. But before removing a, I will check that, okay, instead of removing a, if I remove something else, then what will happen. And so what are the blocks, what are the blocks with whom this a is conflicting? So suppose if I apply again a with this hash function, suppose this is h0, then this is h1, and this is h2, then what so for this obviously the output will be 5, and consider this, for this output is 2 and for this output is 1. Suppose this is written here in this table, you can see here in this table, but assume that this is based on their hash function. So for a is either mapping here in this position 5, and if I go to way 1, then it is placing here with k, and if I go to 3 way 2, then it is mapping here with x. So if I want to remove a, then then in no sorry and which places a can be you can store a can store either here, here or here. So now for y the direct replacement candidates are a, d and m, that is fine. But now for a, what are the replacement candidates? For a you can all the candidates are k and x, right? For d again, if we apply the same concept that I am showing here, instead of a here, if you go for d, then if you go for d, then the candidates will be 3 4 and 1, 3 4 and 1, right? So here so it is b and z, and for m it is p and s, like this. So again, if you go for similar kind of thing for k, then it is l and m, for x it is n, l. So in this way you can go for multiple levels of thing. So now ZK said they will go for multiple levels. So if there are 3 levels, so instead of going for the first one, the skew associative cache will in skew associative cache, if you want to place y, then you have to remove either a, d or m. You'll remove the LRU one among a, d and m. But here what you can do, you can remove LRU of all this. Suppose LRU of all this, so out of all this, suppose if the LRU is n, so let me make it let me remove something, otherwise it will not clear. Okay, now it is clear, so I don't need to remove. Suppose so out of all this, you need to you can remove the LRU. So what you will remove here, suppose LRU is n, so you can remove n. So if you remove n, which one is n here? This is n, right? This one is n here. Sorry, this one is n here, so this is n. So if you remove n, can you place directly y here? No, because y is not mapping in n. So what they are doing here, you can see, when they remove n, in place of n they will remove they will place x, because x can be placed in n. So they will remove n, the x will be placed in n, then a will be placed in x position, and then finally y will be placed in s position. That is showing here. If you go here for y, what they will remove n, and in place of n, x will come here. Okay, and now then the position of x will be empty, so a will go here, and now a is empty so y will be here, and this is showing here in the final list in the right side. So this is how a Zcash works. So here you can say that, sir, how it is solving the local utilization issue. It is solving local utilization issue because it is when it is replacing, it is checking more possible candidates, and from more possible candidates it is selecting the least recently used one. So in this way, if a particular set, though there is no concept of set exists in skew associative cache, but still if there is a particular set which need more space, then it can use more space, because every time we are removing a particular block which is least recently used from a bigger list. So this is how Zcash works. So from your side, for exam purpose, what I want from your side is, you should know the concept of Zcash, which is all the entire concept of Zcash is mentioning here in this picture only thing which is not clear in this picture is what replacement policy they are using. That is explained in the next page, I think, most probably. If I scroll down here, I think it is here, replacement policy. So my expectation from your side is, you will read the paper still experiment section, and you'll understand what is called Zcash. Okay, so today's lecture I have explained a few local utilization issues. There are 2 more local utilization issues that I will discuss in next class, and then I'll go to global utilization issue. Thank you for watching this lecture.